So in the second part of glycolysis, this is known as the payoff phase because this is where we actually begin to see the production of ATP take place, as opposed to the investment phase where 2 ATP were used up, 1 to 2 ATP anyways, and none was made. So again, like the banking analogy, this is where we start to see returns or payoffs from an investment. So at the end of part 1, we saw that glyceraldehyde 3-phosphate and dihydroxyacetone phosphate were the two substrates that we had left as a result of the 6-carbon molecule that we began with going through a series of 4 reactions and then splitting into 2 3-carbon molecules. Now, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate are not the same molecules, and if we want to end up with 2 of the same molecules at the end of glycolysis, we need to convert dihydroxyacetone phosphate into glyceraldehyde 3-phosphate so that we have 2 substrates that are equal. So triose phosphate isomerase is going to facilitate the reaction that will convert dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. And so at the end of that reaction, I didn't write it down twice for space, but there's a little 2 next to every single substrate from now on, just to remind you that there is actually 2 copies of each of these substrates because of the division. So glyceraldehyde 3-phosphate, we now have 2 molecules. And during the next reaction, what's going to happen is we're going to have a new molecule introduced into this reaction. It's called NAD+, and NAD+ is what's called a hydrogen carrier. It carries hydrogens, obviously, after they're stripped from each of the substrates in this reaction. So whenever NADH is involved, we know that hydrogen is going to be stripped from one of the substrates and be carried off by NADH. And NADH will ultimately carry these hydrogens to the electron transport chain. And that is a part of aerobic metabolism. But for now, the important thing to know is that glyceraldehyde 3-phosphate, each molecule of the 2 that we have is going to lose hydrogen, and NAD+ is going to carry it off in the form of NADH. We also have 2 molecules of inorganic phosphate that's going to phosphorylate glyceraldehyde 3-phosphate. And in this step, no ATP is required for this phosphorylation. The phosphate does not come from ATP. However, the enzyme that is going to be used to facilitate this reaction is glyceraldehyde 3-phosphate dehydrogenase. And dehydrogenase is a good indicator that NADH is going to be involved because it's a dehydrogenation reaction that's taking place. So as a result, we end up with 1,3-biphosphoglycerate, 2 molecules of this. And 1,3-biphosphoglycerate is going to be converted into phosphoglycerate. And the reason it's going to convert into phosphoglycerate, 3-phosphoglycerate, is because we're going to strip a phosphate molecule from each of the biphosphoglycerates that we have. Because in this step, ATP will be made. So because phosphorylation is involved, we know that a kinase enzyme will be used to facilitate this reaction. And for step 7, phosphoglycerate kinase is the enzyme that is involved. And so 1-phosphate is going to be stripped from each of these 1,3-biphosphoglycerate molecules, and we'll end up with 3-phosphoglycerate as a result, 2 molecules of it, and 2 ATP molecules will be made using the phosphates that were stripped from the previous substrate. Now 3-phosphoglycerate is going to be converted into 2-phosphoglycerate, and all that has taken place in this reaction is we have moved the phosphate from the 3rd carbon on each of the 2 molecules to the 2nd carbon. So not a lot has taken place, and also some water has been given off in the reaction. And the enzyme that's going to facilitate this reaction is phosphoglycerate mutase. And then 2-phosphoglycerate is going to be converted into phosphoenolpyruvate. So we're almost at the end here, and we're going to be seeing the end product of all of these 10 reactions. But 2-phosphoglycerate was converted into phosphoenolpyruvate using enolase. And then phosphoenolpyruvate is converted into pyruvate using the enzyme pyruvate kinase. And so again, we see the enzyme kinase, and we know that a phosphorylation reaction is taking place, and phosphates will be stripped from phosphoenolpyruvate. So we have 2 molecules. Remember, we've split the 6-carbon molecule that we started with. So 2 molecules, 2 molecules, 2 molecules, 2 molecules here, and then 2 molecules of phosphoenolpyruvate. And so we're going to end up with 2 molecules of pyruvate at the very end of this reaction. So phosphoenolpyruvate is converted into pyruvate, and during that reaction, we've made 2 ATP molecules as well. So we've made a total of 4 ATP in this payoff phase. Now, even though 4 ATP were made, that is not our net production of ATP, because we have to remember that during the investment phase, depending on which substrate we started with, we had to use ATP. So we had to sort of like spend money to make money. So we spent 1 to 2 ATPs in the investment phase, and in the payoff phase, we made 4 ATPs. So if we started with glucose, we know that we had to invest 2 ATP at the very beginning. And so as a result, we have to subtract 2 ATP from the net total that we made, meaning we would have made a total of 2 ATP at the end of this reaction. However, if glycogen was our starting molecule, we know that only 1 ATP had to be spent throughout this whole process. And so if that is the case, then we know that we only need to subtract 1 ATP from the total that we've made. So 4 subtract 1 would be 3, meaning if we started with glycogen, the net total of ATP produced from glycolysis is 3 ATP. So once again, it's important to remember that depending on which substrate we start with, it affects the amount of ATP we've produced. So if glucose is the starting molecule, we're going to end up with a net total of 2 ATP. If glycogen is the starting molecule, then we know that we're going to have a net total of 3 ATP at the end of all 10 reactions. And the final substrate that we're going to be left with is 2 molecules of pyruvate. And pyruvate can eventually be converted into acetyl-CoA and enter the Krebs cycle. And the Krebs cycle is part of aerobic metabolism. So in a way, anaerobic metabolism is able to provide energy both for the anaerobic metabolism through glycolysis, and glucose is also able to provide energy through aerobic metabolism, not directly, but through the conversion of pyruvate into acetyl-CoA, which enters the Krebs cycle, which is part of aerobic metabolism. So as a result, glycolysis is fueling both metabolic pathways through its substrates that it creates at the very end, the ATP and the pyruvate. However, aerobic metabolism is oxygen dependent, and so pyruvate is not always able to enter the Krebs cycle as acetyl-CoA, because ultimately it depends on if there's sufficient oxygen to fuel aerobic metabolism. If there is not sufficient oxygen to fuel aerobic metabolism, pyruvate cannot be converted into acetyl-CoA and enter the Krebs cycle. Because without that sufficient oxygen, then we're going to have a backup in glycolysis. Because what happens is pyruvate gets converted into acetyl-CoA and it runs through the Krebs cycle and it produces hydrogen as a result. And if we don't have the electron transport chain receiving hydrogens from the Krebs cycle and from glycolysis, we have a sort of backup. So it's like a factory that has a halt in production. And so as a result, pyruvate will not go to the Krebs cycle if there is not sufficient oxygen being intaken by the body in order to facilitate the physical activity that's going on. So pyruvate instead will go to what's called lactate. So what happens is NADH will deliver the hydrogens to pyruvate, and through a reaction, pyruvate will be converted into lactate. That way, NADH is freed up and is now NAD+, and able to run through glycolysis and the Krebs cycle to carry hydrogen molecules once again. Because if there is no NADH to carry these hydrogens, then as a result, we just have the free-floating hydrogen in our body, and we don't want that, and so everything gets backed up. But if we can deliver the hydrogens to pyruvate when there isn't enough oxygen, then we have NAD+ free and available to carry those hydrogens. And then pyruvate, because it's converted into lactate, it's not going to be used for aerobic metabolism, so you can cause a buildup of lactate in the body. And some textbooks use lactic acid and others use lactate. Lactic acid is what it becomes in the beginning. So pyruvate is converted into lactic acid, but the natural pH of our bodies causes lactic acid to lose a proton and become lactate immediately, just because of the regulatory pH that is, it's 7.35 to 7.45. And so that pH just causes lactic acid to immediately become lactate. We don't find lactic acid in the body naturally. And so pyruvate has 2 options. It can go to the Krebs cycle, it can go to lactate, and it just depends on the body and on how much oxygen is available to fuel aerobic metabolism, what kind of intensity of exercise the body is performing, and what's the most beneficial, and obviously which is the most energy efficient for the body. But these are the final steps of glycolysis. And remember that this is an anaerobic metabolism, no oxygen is required, but because of pyruvate possibly being able to fuel the Krebs cycle, it is another method to indirectly help aerobic metabolism. And that's it.